Okay. Lesson 2.4 is when we connect the idea of differentiability and continuity. Okay, so we've already talked a lot about continuity in terms of what it means to be continuous, and we talked about that official continuity definition, right? Like the limit from the left has to equal the limit from the right, and the point has to exist at that point, right? So the limit has to exist, and that point has to exist, okay? Now we're going to add in differentiability. So in this lesson, we investigate the difference between differentiability and continuity. Our focus will be to determine when a function fails to have a derivative. We've already talked about that a little bit, but we get into it deeper here. A function that is differentiable at a point is locally linear at that point. Basically, this is telling us that in order for a function to be differentiable at a point, the graph must be continuous and smooth at that point. And that's where we've already talked a little bit about things that weren't differentiable, those sharp points, the cusp. That's where this comes into play, okay? Has to be continuous and smooth to be able to take a derivative. Remember, when we say a function is differentiable, this means the derivative exists, or you're able to take the derivative, okay? So, officially here, differentiability at a point. A function f of x is differentiable at the point x equals c if and only if, and you'll notice there, it's the limit as x approaches c from the left of f of x minus f of c over x minus c equals the limit, which is also equal to the limit as x approaches c from the right of f of x minus f of c over x minus c. So, I remember how I put this into words before, the best way. I mean, you're looking at the limit from the left and the limit from the right is what we're essentially looking at, okay? Let's focus first on how it might fail to exist. And you guys have that part in front of you. I've been short on slides lately, so I'm going to blow this up a little bit. Okay, so how a derivative, f prime of a, may fail to exist. The following examples show us how a function will fail to have a derivative at a point where there is a corner, a cusp, a vertical tangent line, or a discontinuity. So first of all, example 1 here, you have given the graph absolute value of x minus 1. Which, good reminder, absolute value graphs are v's. The minus 1 says the v is moved to the right. Now, what is the derivative, f prime of x, as x approaches 1 from the left? So what am I saying here? As we approach 1 from the left, what is the derivative? Negative 1. Because when I say what is the derivative, I'm asking what is the slope. Good. I purposely didn't say that word, but you guys got it. What is f prime of x as x approaches 1 from the right? It's a positive 1, right? Is f continuous at x equals 1? Why would you say no?
Because yesterday it was d to d.
That wasn't continuous. It was
continuous,
like because the limits.
So it's continuous but not differentiable.
We're getting there, yep.
So
my question here, yeah, is f continuous?
Yeah, because the limits mean.
Yeah, because the limit as x approaches 1. From the left, it's approaching the y value of 0. From the right, it's approaching the y value of 0, and f of 1 is equal to 0. So yes, it's continuous, or I like to go back to the very basic elementary definition of, can I draw it without ever lifting my pencil? And I can. That's awkward to draw a V like that in my brain, but you know, or at least in a graph situation, but you could. Now, is f differentiable at x equals 1? And this is where we're going to say no. And the deal is, it's the limit, and this is where I knew there was something overlooking up top. It's the limit of the derivatives that don't equal each other. So basically, the derivative on the left doesn't equal the derivative on the right.
Because they don't have the same slope.
Right.
That's
Okay.
how you know if they're differentiable.
Huh?
That's how you know if they're differentiable.
Mm-hmm. Yeah. So, like, for my explanation, I put it in the official form since the limit as x approaches 1 from the left of f prime of x, so the derivative, does not equal the limit as x approaches 1 from the right of the derivative. There is no derivative. Okay? I knew the words would come to me. I just had to have a moment. Continuity does the limit from the left equal limit from the right. Differentiability does the derivative on the left equal the derivative on the right. Okay? Let's look at example 2. Given the graph, f of x equals cube root of x. You guys remember that? We haven't done this graph as much, but this is your cube root graph. It's basically the x cubed graph, but sideways, right? Okay, so that's the cube root of x. Good one to know. It will come up. Use the alternate form of the derivative to show that the function has a vertical tangent at x equals 0. So if you guys remember alternate form of the derivative, we're looking at this guy right here. Limit as x approaches c of f of x minus f of c over x minus c. So let's look and see what happens here. The limit as x approaches, what is my c value here? 0. Of f of x minus f of c. F of x is cube root of x minus f of c is cube root of 0 over x minus c, or in other words, x minus 0. Now, if I clean this up a little bit, cube root of x, what's another way to write cube root of x?
Next.
So this is x to the 1/3 divided by x. What's another way to clean up x to the 1/3 over x?
X to the 1/3 times 1 over x.
How can we put the x's together?
X to negative 2/3.
Right? And where do you put a negative exponent though?
Well, wherever it wasn't.
Okay, so, or if this 1/3 minus 1 is negative 2/3, so I'm not going to leave this. It's x to the negative 2/3, or what I'm going to write is 1 over x to the 2/3. I like to think where there's, you know, it's if 1/3 on top and 1's on bottom, there's more x's on bottom, so it's going to have to go on bottom. What do you get when you take this limit?
D.
Okay. I mean, you plug in, you're at 1 over 0. I'm going to use the vocabulary undefined. I'm going to say, therefore, my limit is undefined. Okay. This right here, when we talk about it, we're supposed to be showing there's a vertical tangent line. Do you see how there could be a vertical tangent line? Okay. And by finding that derivative to be undefined, that's also showing that. Okay. It really sounded like you threw your book on the floor for a moment. I don't know why, but just the way it flopped. So it sounded like. Okay.
Not this way.
3. Given the graph, f of x equals 1 over x plus 2 squared. First of all, describe the derivative of f as x approaches negative 2 from the left and the right.
Both going towards the Sure.
Okay, the limits are going towards infinity,
So the derivatives
but what's the derivative doing?
infinitely, so
Infinity and then 0.
So let's look at both sides here. We're going to look as x approaches 2. Wait, it's not 2, is it? It's negative 2. As x approaches negative 2 from the left, and as x approaches negative 2 from the right. I want to know what the derivative does. So when I'm going to say derivative, I'm going to say, what does f prime of x do? Okay, I'm going to use that notation. As we approach negative 2 from the left, so that's on this side of the graph, yes? What kind of slopes do we have there? Derivatives are slopes of the tangent line. Well, your slope on that, huh?
very big ones.
Very big ones. Positive, negative, positive, yes. My entire, on the left side of negative 2, all my slopes are positive, aren't they? This line is always increasing. It starts very close to 0, right? You're very close to having a 0 slope. And then as this gets up, my slope gets very, very steep. And so what is my slope doing on the left? It's approaching positive infinity. Okay? Now, on the left, as we approach from the left, what are we starting off very close to?
0.
Very close to 0. What do you notice about the slopes on this side? Okay. Why negative infinity? Are all my slopes negative here?
Yeah.
Okay. I mean, if we go from left to right, this is a decreasing graph. These are all negative slopes. We're really close to 0. Okay. So say negative 1, or yeah, really close to 0. So say negative 1/10, but then as you get here, somewhere in here, there's a negative 1. But then these numbers are going to become bigger and bigger and bigger, aren't they? So this is approaching bigger and bigger and bigger, but in the negative sense, which means negative infinity. Okay, now, right there, because the derivative on the left does not match the derivative on the right, I'm going to say, therefore, this function is not differentiable at x equals negative 2. Okay? That's what that first part A tells me. Now, so part A was based on the graph. Part B, given the derivative, So they gave me the function, and they gave me a function graph. Now, given the derivative, use the formula to evaluate the derivative when x equals -2. So, well, first of all, if I put -2 in there directly, -2 plus 2 is 0. We have 0 in the denominator. We can't do that. So we're going to have to look at this from the left and the right again. So we're going to evaluate our derivative. Let's start with -2 from the left. If I evaluate with -2 from the left, -2 over, what do I put in place for x if we're coming from the left of -2? No.
Negative.
No,
-2.01.
because we're on the left of -2. Hey, I had to check myself too.
I do
So.
right to left. So.
Now, in my notes, I'll be honest, I just have -2.1, but something like that, right? So if we put -2.01 plus 2 raised to the power of 3. So -2 over, this is going to be what? -0.01 raised to the third. What are we going to have here in terms of signs? The top is a negative, yes?
The bottom's also going to be negative.
So somehow or another, we're going to have a negative divided by a negative. Fair enough? Okay. I'm not doing the math. But a negative divided by negative is going to result in a positive. 2 divided by a decimal that's getting smaller and smaller and smaller. What is 2 divided by that decimal? It's approaching what? Positive infinity? Because this would be 2 divided by 0.0001. No, 0.001. But 2 divided by 0.0001, you're getting a bigger and bigger number. So we're approaching positive infinity. Does that kind of match with what we found up above? Yeah. Now let's look at it from the other side. Let's evaluate the derivative from the right side of -2. So -2 over, now we can use your -1.9 or -1.99 plus 2 quantity cubed. So -2 divided by, well, -1.99 plus 2, positive 0.01 cubed. And what are we going to have this time? A negative divided by a positive, which is a negative. What's 2 again divided by a increasingly decimal with more and more zeros? That's going to be negative infinity. Okay? So notice, answers from the first part, looking at the graph, agree with answers from the second part, using the derivative formula and plugging some things in. Okay? Between what we found up there and what we found down here, we can definitely say that the derivative at -2 does not exist. Okay? The derivative on the left does not equal the derivative on the right. It definitely does not exist. Okay? Now, that leads us into, okay, in this particular problem, was this continuous? Can I draw this graph with one pencil swipe? No, this graph is not continuous. It's 2 separate pieces. If it's not continuous, it can't be differentiable. If you can't tell me it's a continuous, you shouldn't even have to ask yourself about differentiable. The automatic answer is no. Okay, so differentiability implies continuity. So what we get out of this, which is really handy to know, if a function is differentiable at a point, then it is also continuous at that point. Okay?
What about the first page? We just forget about it.
I don't know what's on the first
It
page.
was
That's,
continuous but not different. Or talk about if it's
yeah. Okay, and that's where, give me a moment here. Yep. Okay, I was trying to think, which one's on the first page that you're unhappy about? So, if it's differentiable, it is definitely continuous. Now, so if a function is differentiable, it is continuous. So differentiability applies continuity. So if I tell you, yes, this function is differentiable, you can automatically check off in your head, it's also continuous.
I got stupid. Squares are rectangles, but rectangles aren't squares.
Okay. It is possible for a function to be continuous and not differentiable. So just because I tell you something's continuous, you don't get to automatically say, oh, so it's differentiable. No, that's a no-go. Okay? So, differentiability implies continuity. However, continuity does not imply differentiability. Okay? Sharp corner, cusp, or vertical tangent line, or discontinuity. Those are things that are going to break and it's not going to be differentiable. Sharp corner, cusp, the same thing. Vertical tangent lines, those are not, they could be continuous, but they won't be differentiable. Discontinuity means it's not continuous, so definitely won't be differentiable. Okay, how do you feel about your geometry days?
Pretty good.
Okay, it's good because I don't think I've ever taught, well, maybe once. Do you remember what a contrapositive is?
Yep.
I remember doing proofs. Is it?
I mean, at one point you probably had to talk about converses, inverses, contrapositives. Like that's all a geometry thing.
I remember talking about it.
Okay. Well, because this next problem asks us to write the contrapositive to the statement. If a function is differentiable at x equals c, then the function is continuous at x equals c.
So is it if a function is not differentiable at x equals c, then the function is not continuous? Because that's just
That's not true.
No? So it's the knots, but you also have to flip it.
So if a function is not continuous at x equals c, then the function is not differentiable.
Oh, I remember that.
Mm-hmm.
We did it briefly, but it was like very simple.
Yeah.
No, we did. In geometry, we did that a whole lot. I remember failing that unit.
No, you're right. They got just in the same.
But it was the one right around that. It's the same question.
If the function is not continuous at x equals c, then the function is not differentiable at x equals c. Okay? So, you can say if the function is differentiable, then it follows that it is continuous. Or if the function is not continuous, then we know it's not differentiable. Must be continuous to be differentiable. Does not have to be differentiable, though, if it's continuous. Okay. Question 4 when you're ready. Describe the x values at which the function g of x equals the absolute value of x squared minus 5 is differentiable. Justify your answer.
So, from negative 2 to positive 2, that's a lot. Is that right?
Say it again.
From negative 2 to positive 2, roughly.
What else?
Negative infinity to -2. Well, that doesn't work. Oh, because it's the absolute value. I was sitting here, I was like, they're never going to be the same, but it's absolute value.
Yeah.
So, yeah, from negative infinity to about negative 2.2 and 2.2 to infinity, and then negative 2. So basically the whole thing.
Except for those points.
Yeah.
Okay. Now, officially, those points, if you take x squared minus 5 and set it equal to 0, add 5 over, x squared is 5. What are those points? Square root of 5 and negative square root of 5, of course. Okay. And then you guys already found your problem areas, yes? So let's put this in interval notation.
Oh, this is square root.
Which square root of 5 is like 2.2 something, I think.
Yeah.
2.25, 2.24. I could be off on that, but.
That's why we have parentheses.
Okay, so starting on the left, we start being differentiable all the way to the left. So negative infinity up to where? Or I'm going to write negative square root of 5. Okay. With this negative square root of 5, we're going to use a parenthesis because it is not differentiable at that specific value. I'm going to use union. And then now where do we pick back up? Negative square root of 5, again with a parenthesis, comma. Now how far are we going? Positive square root of 5, parenthesis, union, and then square root of 5 to infinity. What's my justification?
Because we said so.
Sharp corner or cusp. Okay. I have, since g of x has a sharp corner or cusp at x equals negative square root of 5 and positive square root of 5. Okay, so yeah. Since g of x has a sharp corner or cusp, I'm going to say at x equals, I'm going to say plus or minus square root of 5. Okay. Good. Okay. The key here is we had to check our problem areas. And that's what I'm going to keep telling you to do, is check the problem areas. These were problem areas because we saw those sharp points, didn't we? Okay. And as you look at those, we'd have negative, we'd have positive. We'd have negative, we'd have positive. Okay. 5. Find all the values of x for which the function is differentiable. What do we know about these individual pieces of this piecewise function?
They're all continuous.
X plus 1 squared is continuous. It's a parabola. 2x plus 1, it's a line. 4 minus x squared, another parabola. Individually, they're all continuous, yes?
Yep.
So what do we need to consider?
Like where there might be a sharp corner cusp or vertical tangent line.
Okay. But even before then, do we know for sure this graph as a whole is continuous? we know those individual pieces are continuous, but
Can be
as a
counted.
whole, is it continuous?
Yeah.
So what numbers, specific numbers, do we need to check? 0 and 3. Yes? Okay. So let's see what's going on at x equals 0 and x equals 3. How are we going to know if it's continuous at x equals 0?
Plug 0 in to the first one.
Okay, to the first one. So we want to know, does x plus 1 squared equal 2x plus 1? What do we end up with? 1 equals 1? Okay. So there, it's at least continuous at 1, yes? Okay. What about x equals 3? Yeah, we want to know, does 2x plus 1 equal 4 minus x squared at x equals 3?
Absolutely no.
Okay.
17.
So at x equals 3, we definitely have a problem, yes? At x equals 3, my graph is not continuous, which means it cannot be differentiable at that point. Okay? Now,
Negative infinity to 0 would be different. Because it says find all the values.
well, more than that.
Just negative infinity to 3, right?
And then
Three.
from 3 to infinity.
Infinity.
Basically, we just need to exclude the value of 3. Okay, because it's not continuous there, so it's not going to be differentiable there. So I'm going to say that h of x is differentiable at negative infinity to, it was positive 3, isn't it?
Yeah.
Positive 3 and
3 to infinity.
3 to infinity. 1 was okay because it was continuous. The only thing you kind of have to think about is, I guess there is a slight possibility it could be a sharp point or a cusp there, depending on how they connect. But we're just going with this not for right now. Okay? I'm going to write down there is a discontinuity at x equals 3. So h of x, is not differentiable there. It's not continuous. It cannot be differentiable. Huh?
I don't think we'll have time for the bottom of it.
Probably not. Let's see.
Okay, we're exactly halfway through, so.
Piecewise functions are always challenging. Not only do the limits of the slopes need to be approaching the same value on either side of a given x value, but the function must be connected and smooth, and this is what I was just referring to, in order for the function to be differentiable at the given point. So continuity is the easier piece to check. The making sure it's smooth is the harder piece to check, okay, to make sure it's differentiable. What 6 asks us to do, find the values of the constant where the function is continuous over all reals. Is that a Monday thing?
I just don't want to rush through it and not fully
True.
understand it.
Yeah.
We got halfway through with talking about homework for a couple minutes.
Yeah, we should be. Yeah, we should be okay. So we will come back to that Monday.